Dear students, in today's session we will discuss about the dynamic programming. This is one of the algorithm design strategy like divide and conquer and greedy approach. We will see what you mean by dynamic programming. In dynamic programming, we will be having overlapping subproblems and the solutions of the smaller subproblems will be merging and that will be from that we will be getting the final given problem solution. And the smaller subproblems result will be recording and that can be reused for solving the other problems. In dynamic programming can be used when the solution to a problem can be viewed as a result of sequence of decisions. Dynamic programming is used for optimization problems like minimization and maximization problem. And in greedy approach, it is not guaranteeing always the optimal solution, but dynamic programming is always guaranteeing the optimal solution. So these are the major points. It will be having overlapping subproblems. And from that subproblem solution, we will get the solution for the given problem. And the subproblem solutions will be recording. And instead of recomputing the subproblem solution again and again, we can just use the result and it involves a sequence of decisions. And that is called the principle of optimality. So we will see why this overlap, what is this overlapping subproblem and how it will be useful for getting the solution of the final one with the help of one example. All of you are familiar with the Fibonacci numbers. So it is like f of 0 is equal to 0, f of 1 is equal to 1, that is the initialization part. Any nth term you can calculate by adding the n minus 1th term and n minus 2 second term. So it will be like there are two different approaches. One is called a top-down approach and another one is called a bottom-up approach used for calculating the nth Fibonacci term. For example, f of 5 I want to calculate. In top-down approach, it will be calculating from f of 5. For that, f of 3 and f of 4 is required. Then f of 2 and f of 1 is required. Like that, the process will be continuing till f of 0. That means from 5 to 0, we are calculating. And in bottom-up approach, we will be using from 0 to 5, we are calculating. Look into this recursion graph. There f of n can be calculated from f of n minus 1 and f of n minus 2 and f of n minus 1 is getting through from f of n minus 2 and f of n minus 3 and f of n minus 2 will be getting from f of n minus 3 and f of n minus 4. The first property was it will be having overlapping subproblems. So what do you mean by that? F of n minus 3 I am calculating twice, one for getting f of n minus 1 and one for getting f of n minus 2. So once that is the subproblem which will be common for calculating f of n minus 1 as well as f of n minus 2. So once I have calculated this value, that will be storing, and that from that stored location, when the second time I need f of n minus 3, instead of recomputing it, I am just using the result which was calculated in the previous step. Similarly, you can see f of n minus 2 is used for calculating f of n minus 1 and f of n. F of n minus 2 is used for calculating f of n minus 1 and f of n. So that is my mean by overlapping subproblem. And the result, what is the relevance of storing the intermediate result? Instead of recomputing it, you can use it in the next step. So this is the bottom-up approach for the same. So f of 0 and f of 1 will be 0 and 1 respectively. That is the initialization part. That will be storing in a location. With that f of 2 we will be calculating. We are accessing f of 0 and f of 1 and we will be getting f of 2 as 1 and the result will be recorded on a table or in a memory location. Based on that table, it will be already having values like 0, 1, 1, that is f of 0, f of 1 and f of 2. Then f of 3 will be calculating is just accessing to memory location and sum. So it is like 1 plus 1 is equal to 2. That means f of 1 is 1, f of 2 is 1, and the result is calculated, and f of 3 will be recorded in the memory or in the table. And this process will be continuing till you will be getting f of 5, and that will be recorded on a table. So whenever you need any value like f of 3 or f of 2, it will be just checking the table whether the entry is present or not. If the entry is already present, it will be just taking the value and computing for the given problem. So overall, we can tell that dynamic programming is having smaller overlapping subproblems, and it will be calculating the solution of the smaller subproblem only once, and it will be recorded, and the final state of the table, which will be the solution for the given problem. So the process problem will be solving in step by step by taking different decisions. What should be done? Whether I should add, what is the procedure I should follow? So that is the decision it will be following, and the result will be computing, and it is recording, and it may contain multiple overlapping subproblems. That are the properties of a dynamic programming. We will see one of such problem called transitive closure of a directed graph, which will be calculating with the help of Warshall's algorithm. We will discuss about what you mean by transitive closure and how can you calculate the transitive closure using Warshall's algorithm. So before that, what is transitive closure? Just look into the definition. Transitive closure of a directed graph with n vertices can be defined as an n-cross-n Boolean matrix Tij, in which the element in the ith row and jth column is 1 if there exists a non-trivial path between I and j. Otherwise, Tij value will be 0. It is very simple. Just look into the diagram. That will give you a clear idea about what you mean by transitive closure. Already you have studied about transitive closure of relation. If A is related to B and B is related to C, then transitive closure property will be telling that A is related to C. The same thing here also. The graph, whatever is given, is a directed graph. We know that the directed graph can be represented in two different ways, adjacency matrix and adjacency list. And here we are worrying about the matrix format. So we are representing the given graph in the adjacency matrix. How can you represent a given graph in adjacency matrix? If there is a direct connection between two vertices, we will be denoting it with 1. In those location will be denoting with 1, otherwise the value will be 0. Look into this. Just going through quickly, how can we represent a graph in adjacency matrix? That we have already studied in our data structure session. So A to B, there is a direct connection. So I have kept 1. A to A, there is no self loop. So I kept 0. A to C, there is no direct path. So I kept 0. And A to D, there is no direct path. So I kept 0. Similarly, B to A, there is no direct path. A to B path is there, but it is a directed graph. So there is no B to A path. B to A direct connection. So that is 0. Then B to C, there is no direct edge. So it is 0. B to D, there is an edge. So that will be 1. Similarly, the remaining things. From C, you don't have any other outgoing edge. So then complete entry will be 0. From D, D to A is there. D to C is there. D to B, there is no direct connection. D to D, there is no self loop. So those two entries will be 0. Now we will be looking into what you mean by transitive closure. What is this definition is telling me? The definition is telling if there is a path existing between I and j, the entry value will be 1. Otherwise, the value will be 0. What do you mean by the path? If from a source to destination there is a path, means there is a set of vertices you can go through. From the source vertex to the destination vertex, there is a connection. So we will see from A to A, is it any path existing by traversing a set of vertices? Yes, there is a path. A, B, D, A. There is a path. So I can keep, if a path is existing, then the value will be 1. Otherwise, the value will be 0. Then A to B, there is direct connection is there. So you can directly give what path is existing. Value will be 1. A to C, is it any path existing? That means I should start from A, I should reach C by traversing a set of vertices. A to B, B to D, D to C, a path is existing. So A to C, there is a path. From A, I should start, I should reach C. That is possible. So I can write 1. A to D, that is also existing, A, B, D. So I can keep 1. Similarly, B. B to A, there is a path. B to B, there is a path. And B to C, there is a path, BDC. And B to D, direct connection, so 1. All the values will be 1 because the path is existing. Then from C, C is not having any outgoing edge, so there is no path existing from C as a source, and other vertices should be destination. So there is no path existing. Then from D, you know, D to A, there is a connection. D to C, there is a connection. D to B, there is a connection. And D to D, there is a connection. So from all the edges, you can keep as 1. So that will be the transitive closure, and that is an encroach n matrix, and which will be representing the paths existing in the given directed graph. So the transitive closure is also called path matrix. The common way for finding the transitive closure. You have already studied about the graph traversals algorithms like DFS and BFS that you can apply to the graph so that you can find out what all are the paths existing in the graph. But that is little time consuming. So we are going with some other algorithm that is called Warshall's algorithm, and it will be working based on the dynamic programming approach. So for that, it is using a set of encroach and Boolean matrices like R0, R1, R2, etc. to Rn, where Rn will be your final resultant transitive closure matrix. R0 is your adjacency matrix, that is the input you are giving to the algorithm. R1 will be based on R0 and R2 will be based on R1. Like that, this, in each step, you are finding a new path in, or a new set of paths. We will see the details of Warshall's algorithm. So Warshall's algorithm is used, this is the given graph for finding the transitive closure. So this is a given graph and that has represented in the adjacency matrix format. After applying Warshall's algorithm, I will be getting a path matrix which will be having the other connections or other path which are existing in the in the graph. So 2 to 2, there is a path existing that is like 2 to 4 and 4 to 2, that is a new path. And 2 to 1 and 1 to 3, there is a path. So 1, 2 to 3, there is an edge. So those two entries I have updated. Then from 4 to 1, there is a path existing. There is no direct path. That's why 4 to 1 we kept in the adjacency matrix as 0. But there is a path existing. I can start from 4. I can reach 1 by traversing a set of edges. Like 4 to 2, 2 to 1. So I have updated in the path matrix as 1. Similarly, 4 to 2, that is a direct connection. It was already 1 in the adjacency matrix. Similarly, 4 to 3, there is a path existing. So you can just keep that as 1. And 4 to 4, there is a path existing, that is 4 to 2, 2 to 4. So that will also update it to 1. So this is the final transitive closure value. We will see how Warshall's algorithm will work. The main idea is, if there is a path existing between I and j, if and only if, either there is a direct connection between I and j, or there is a path existing between I to j, which should be going through vertex 1, or there is a path existing between I to j, which should be going through vertex 1 and vertex 2, or only to vertex 2, there is a path existing between I and j. So in each time, we are adding one intermediate vertex and checking whether there is a path existing between those two vertices. So this is the input graph I am having, and the corresponding adjacency matrix, or the input what we are giving to the Warshall's algorithm, is the adjacency matrix. As I told you earlier, R0 will be representing the adjacency matrix of the given graph. So the given graph adjacency matrix I have marked as R0. Now you listen the steps carefully. In first step, you take first row and first column. So I have selected the first row and first column. Now I should construct R1 from R0. So the first step, whatever the value present in the first row and first column, directly you can copy paste to R1. And the remaining elements like 001, 000, 100, in that elements, wherever you are having 1, that you can directly copy to R1. And other elements, that is the zeros present in this part, you should check whether what should be the value come if I am doing logical AND operation. 1 and 0, both of these entries, that is the selected row and column entries, you should see, and its AND operation result will be 0 or 1, you should see. 1 and 0 you are checking, so the result will be AND operation, both should be 1, then the result will be 1. So 1 and 0 you are checking, so the result will be 0. Then 1 and 1 will be checking, so this will be changing to 1. This is already 1, no need to cross check. Here, 1 entry is 0, so no need to check. 0 to 0, 0, 0 to 1, 0, 0 to 0, 0. Then 0 to, this is already 1, no need to cross check. 0 to 1, 0, and 0 to 0, 0. So the AND operation between the first row elements and first column entry corresponding to a specific element we are checking. So for this location, you are having 0 as the row number and 1 as the column number. Its AND result will be giving me 0. Now the next entry. So I should construct R1. So only one updation I have done, that was 1 to 1 and operation result was 1. So I have updated with 1. So it means that I have considered vertex 1. With the help of vertex 1, I find out a new path existing between 2 and 3. That I have updated to 1. In my next step, I should construct R2 from R1. Now I can just leave R0. From R1, I should construct R2. For that step, what is the row number and column number I am selecting is second row and second column I should select. So R2 will be having the elements of second row and second column of R1 as it is. And the remaining elements, like wherever the 1 is present, that will be directly copied. So here only 1 is present at this location, remaining all are zeros. So that one directly will be copying along with this column and row number. And other zeros, I should check whether it is 0 or 1 based on the logical and operation. 1 and 0, that is the location. So the row number and column number will be taken. So 1 and 0, result will be 0. Here you will be getting that will be 0 and 1 against 0. This location you will be getting 1 and 0, 0. This will be 1 and 0, 0. And this will be 1 and 0, 0. And what about this? This will be 1 and 1. So this will be updated to 1. And this will be again 1 and 1. So this will be updated to 1. And this 0 will be again, its row number is 1 and column number is 1. 1 and 1, logical and operation, result will be 1. So the last row completely will be changing to 1 and the remaining elements will be keeping as it is. Now I should construct R3 from R. Now I should construct R3 from R2. So in the step, you need to select third row and third column. So third row and third column will be directly copying to R3 as it is. And wherever the 1 was remaining, so this one, these two, 1 and this one will be directly copying to R3. And other zeros will be checking whether any change for the value. The 0, 1 and 0 is doing AND operation, it's not updating. 1 and 0 is doing AND operation, not updating. This is 1 and 0 is doing updation, no updation. So other values are already 1. There is no updation is happening in this stage. And this one more 1 is 0 is present. So but 1 and 0 is doing AND operation, no updation. So the value as it is will be remaining in R3. Now I should construct R4. So for that, which row and which column I should select? Last row, that is fourth row and fourth column I should select for calculating R4 from R3. So R last row and last column I have selected, and that value directly will be copying to R4. And wherever you are having 1, here you are having 1, 1, 1, 1. These three 1 will be directly copying to R4, and other zeros I should cross check. The 0, 1 and 0 and result will be 0. 1 and 0, result will be 0. And this is 1, no need to check. This is, its row number will be 1 and its column number will be 1. So 1 and 1 will be doing AND operation. So the result will be 1. So this will be updating to 1. And these values, that is 0 and 1, that is the location. So this will be 0 and this will be 1 and 0 and operation result will be 0, and then 1 and 0 and operation result will be 0. So this entry will be updated to 1 and remaining will be keeping as it is. And this will be the final R4 I am having. So this is the final transitive closure of the given input graph. So the R4, whatever you have calculated from R0, that is the transitive closure of the given input graph. I think you got the procedure. Now we'll see one more example. A, B, C, D. The graph we have already seen. So the first it's adjacency matrix, that is your R0. From that you should select the 0th row and 0th column. That as it is you can just copy paste, and wherever 1 is present that you can just keep as it is, and other zeros you should check what value will come. This 0, 1 and 0 and operation result will be 0. This is again 0. This is also 0, and this is 0, and this is 0 and 0 0, and this value 1 and 1. So this will be updated to 1. And what about this? And that will be 1 and 0. So its result will be 0. So this value will be updated to 1, and other parts will be as it is. Now in the second step R1, I should select the first row and first column, and that will be directly copying to R2, and other values wherever the 1 will be present, that will be directly copying, and other values you should cross check whether it will be changing or it will be keeping with the same value, that is 0. So in that case, you will be getting two updations, that is this value will be updating this one, and this one and operation will be doing, and it will be updated to 1, and the last one, this one and this one will be change doing the AND operation. Those 0 will be, this 0 will be updated to 1. And now I should select the third row and third column, that will be directly copying to the result, and there is no updation is happening at this point. Remaining values as it is will be keeping, and I should select the last row and last column, that is the fourth row and fourth column for calculating R4. In this step, wherever the locations will be changing, wherever the value 1 will be present, that will be keeping as it is. And again, this will be 1 and 1, so this should update to 1, and this will be again 1 and 1, the result will be updating to 1. And what about this? That will be 1 to 1, there is a path existing, so that will be 1, and 1 to 1 and operation result will be 1, and 1 and 1, the and operation result will be 1. And this is with respect to 0, so though these entries will be keeping as 0, and other locations will be updated with value 1. And that should be the final thing. And you can see there is a path existing between A to all other vertices, B to all other vertices. From C, there is no connection or no path to other vertices. And even from D, there is a path existing from D to all other vertices. So this will be the final transitive closure of the given graph. So the basic idea of Warshall's algorithm is, if there is a direct connection between I to J, that will be keeping that a path is already existing. Otherwise, we will be going through k different states, so k different intermediate nodes, and with that is there a path existing between I and J is the key. If it exists, then we will be updating the path matrix accordingly. So in the case stage, determine if the path existing between two vertices I and J using just vertices from 1 to k. So in Rk of Ij, that Rk of Ij, or for example R3 of Ij, will be based on R2 of Ij. So few values, whatever was existing from R2 of Ij, we will be keeping as it is, and few we will be checking based on there is a path existing in the previous stage from I to k and from k to j. In the previous step, if you find out a path existing between I to k and k to j, then you will be doing the AND operation over there, and that will be updating with the Rk of Ij. So if the path was already existing, whatever was there in the previous stage, that will be directly taken. And if there is no path was existing in the previous stage, and but there was a path existing from I to k and k to j in the previous stage, then that will be updating in Rk of Ij. So this is the Warshall's algorithm. The input given to the Warshall's algorithm is the adjacency matrix of the diagram, and output is a transitive closure. And R0 we will be keeping A, that is the adjacency matrix you have given. And K is equal to 1 to N. What is that K? K is, we will be calculating different N cross N matrices. So we will be calculating N vertices, N matrices. So that means if in the previous example you had 4 vertices, so you calculated up to R4. So if you have N vertices, you should calculate up to Rn. So Rn. So K should be varying from 1 to N. And for accessing the matrix, you need two indices, I and J, that will also starting from 1 to N. So that there is, this was telling that this is the only line which is explaining the Warshall's algorithm. Rk of ij we will be getting either from Rk minus 1 of ij, that was already existing, path was already existing in the previous step itself between I and j, that you will be directly copying to Rk of ij. Or if that was not the case, you will be checking with R in the previous step, that is R of k minus 1. There is a path existing between I to k and k to j. If that was existing, it will be doing the AND operation and the result will be storing in the Rk of ij. And finally, that process will be starting from 1 to n. That means R of n will be calculating at the end, and that will be returning. That is the final state you are having, and that is returning from the algorithm. How many loops are present in this algorithm? 3 loops, all are varying from 0 to n. So the order of this algorithm will be order of n cube. We can implement bitwise operators in the modern systems. So it will be making the system more fast for a larger graph for finding the transitive closure or path matrix. In each time you are recording the intermediate result, that is little extra space is required for this algorithm. That's all about Warshall's algorithm. Thank you.